Hi, this is Tzvi Rosen. In this lecture, we're going to talk about computing the volume of solids of revolution using the method of cylindrical shells. In the last lecture, we spoke about computing the volume of solids of revolution by taking slices perpendicular to the axis of rotation and then revolving them around the axis of rotation, giving us disks or washers, depending on whether you're up against the axis of rotation or not. So you can see that because we're perpendicular to the axis of rotation, what comes out is a flat washer with kind of a long wall. It's not just it's not a thin circle. The circle is thick, and it's the height that's flat. In this lecture, what we're going to talk about is taking slices parallel to the axis of rotation. As you can see here, this golden rectangle is parallel to the axis of rotation. And when we rotate that around the axis of rotation, we get a cylindrical shell. So there, the wall is very thin, but it's quite tall. So contrasting to the washers are flat but thick walls, and the shells are thin-walled but tall. Why do we need this? Okay, we already know how to use disks and washers, so why are we trying to compute volume with these parallel slices as well? Why aren't the perpendicular slices enough? So this example illustrates why we would prefer to have to be able to use parallel slices. So let's say we're asked to revolve this region around the y-axis. Okay, so if we wanted to use slices that were perpendicular to the axis of rotation, it would be slices like this. So looking at this slice, first of all, it's not a solid washer. We're going to have these two non-contiguous regions. So it'll come out looking like a disk inside of a washer. And that's not very nice to look at. Okay, it's like that target symbol. But even if we were to allow that, we also don't know what this length is. Right? There's no great way to describe this x value except to say that it's one of the roots of this polynomial defining the curve. Similarly with this length, it's just the difference between two of the roots of this equation. On the other hand, if we take a parallel slice, okay, so this is parallel to the axis of rotation, which is this, which I'm dotting in orange right now. It's in one solid piece. It's got a height that I can easily describe just by using this equation, right? This height is this value for any given x. So the parallel slice is, in this case, much easier to use than perpendicular slices. Okay, so parallel slices are sometimes easier to describe, but how do we get the volume of the shell corresponding to that parallel slice? So we do this by drawing a picture of what's going on. We have that rectangle becomes like the wall of a cylinder, and it corresponds to removing, this volume corresponds to removing the smaller cylinder from the left side of the rectangle, and removing that from the volume of the slightly larger cylinder that you get from the right side of the rectangle, the right side of the slice. So computing that volume, we know that the volume of a cylinder is pi r squared h. The slightly larger cylinder has radius r plus dr. Okay, dr is our symbol for an infinitesimal length in the radial direction, so going out along the radius. And then from that we subtract pi r squared h with just r, not with the dr. And you can see why that's happening from this picture. And just manipulating these symbols a bit, we find pi times 2r dr plus dr squared h And since dr is very small, dr squared is relatively negligible. So what we're left with is dv, this infinitesimal volume, is equal to 2 pi hr dr. Okay. Another way of remembering this formula, instead of thinking of a difference of cylinder volumes to obtain our infinitesimal volume, which is dv equals 2 pi hr dr, we can also think of it as a rolled up rectangular prism. And you can see this is our rectangular prism. It's kind of like the label on a can, on an aluminum can, if you unroll the label. And you can see in this image, if we slice this cylindrical shell, what we end up getting is a rectangular prism with thickness dr, height h, and length equal to the circumference of the circle, which is 2 pi r. Okay, so now we have our formula for an infinitesimal volume, and that's dv equals 2 pi hr dr. Now the r variable can be thought of as distance from the axis of rotation to wherever you are in your region, and each rectangle is specified by an r value. When we compute our integral to compute the volume based on the infinitesimal volume, the bounds of the integral are going to be r min, the smallest r value in the region, and r max, the largest r value in the region. And that's indicated in this image based on the smallest radial value and the largest radial value in the region that we're rotating. Now the formula for the volume of the solid of revolution is v equals integral from r min to r max of 2 pi hr dr. When we're rotating around axes, this takes a special form. So if h is h of x, and that's some function of x, and we rotate around the y-axis, so let's give a quick picture of what's happening here. So we have some region here, and we have a function h which tells us how high this is. This is h of x, and this is x, right? So the height of this rectangle depends on the x value. Then the integral we would use to compute the volume of the corresponding the corresponding solid from rotating around this line is given by the integral from x min to x max of 2 pi x h of x dx. Okay. In a similar way, if we're rotating around the x-axis, and we have some region here, we're going to consider h of y, the height of this rectangle, as a function of the y value. Okay, and this is h of y, and we are and the distance from the axis of rotation is y. So the formula for the volume in this case is integral from y min to y max of 2 pi y h of y dy. Okay, now let's compute some actual examples. Let R be the region enclosed by y equals 4x minus x squared and y equals 4x. Find the volume of the solid obtained by rotating around the y-axis. Okay, so first step, I always like to draw the region and the axis. So that's what we're going to do first. Okay. So let's first draw the lines, the line y equals x. That's very simple. It's just a nice diagonal line. And now we're going to try and draw y equals 4x minus x squared. So because it's a degree 2 polynomial, we know it's a parabola. And just looking at this, it's easy to factor. We can factor out x, and it's x times 4 minus x. That means at x equals 0 and x equals 4, 1, 2, 3, 4, this parabola is going to intersect our curve. That means its highest peak, its peak is between them, And again, we know it's pointing down because the coefficient of x squared is negative. So the peak is at 2, and when x equals 2, y equals 4. So we have 1, 2, 3, 4. And we have a parabola shape here. And this is our region. Okay. And now in terms of which axis we're using, we're told to rotate around the y-axis. So we're going to rotate like this. Okay, and if we wanted to give ourselves a little sketch of what the solid would look like, it'll be something like this. It's a little bit like a cone with a rounded top. Okay, so the next thing I want to do is draw the slice. Okay, so we're going to be using the method of shells here. So our slice is going to be parallel to the axis of rotation. Okay. And the next thing we want to do is label, H, R, and dr. Okay, so our H is given by the height of this rectangle. To get the height, we would subtract the higher y value minus the lower y value. So the higher y value is 4x minus x squared, and the lower y value is x. Okay. R is going to be x in this case because it's distance from the y-axis, and dr is going to be dx. Okay, the next thing we want to do is find bounds for the integral. Okay, so on the left end, it's pretty clear that it's x equals 0, or r equals 0. So r min is 0. On the right, we have to figure out where these two are equal. Well, when these are equal, we know 4x minus x squared will be equal to x. But that's the same thing as saying that x squared minus 3x equals 0. And that means that x is equal to 0 or 3. So the other intersection point will be x equals 3. So r max equals 3. Okay. So let's add another page in. So here's where we're going to do our integration. So we have v will be equal to the integral from r min to r max of 2 pi hr dr. And we got all these values in the last slide. Integral from 0 to 3 of 2 pi. Okay, r is x, I'm sorry. H is 4x minus x squared minus x. And we multiply that by dr, which is equal to dx. Okay, we can pull the 2 pi out of this integral. Oops. And then we have integral from 0 to 3 of, let's combine these, so it's 3x minus x squared, so it's 3x squared minus x cubed. Seems having some technical difficulties, apologies for that. 3x squared minus x cubed dx. And can apply the power rule here to obtain 2 pi times x cubed minus x to the 4th over 4 from 0 to 3. which gives 2 pi times 27 minus 81 over 4, and the evaluation at 0 gives 0, so we just have to simplify this, and it's equal to, so the 81 is 27 times 3, so it's 27 times 4 over 4 minus 27 times 3 over 4, so it's 27 over 4 times 2 pi is 27 pi over 2. Okay, and you can consult a calculator to do that if it's helpful. Okay, let's try another example. We'll let R be the region enclosed by xy equals 1, x equals 0, y equals 1, and y equals 3. And we would like to find the volume of the solid obtained by rotating R around the x-axis. So again, as before, start by drawing the region and the axis. Okay, so we have xy equals 1 is a hyperbola, if that sounds familiar. If not, you could graph a few points until you've got an idea of what it looks like. X equals 0 is the vertical line here. Y equals 1 is this line. And y equals 3 is this line. Okay, so clearly our region is this funky region here. Okay, and we're going to be rotating around the x-axis, so that's this axis here. Okay, and if we want to get a sense for what that might look like, it'll be something like so something like this. Kind of like a volcano, I think. Yeah, in any case. Okay, that's step 1. Step 2, draw a slice. So for that, we've got to think again, we're using shells, so we want to be parallel to the axis of rotation, and that puts us here. Okay. Step 3, label H, R, and dr. So here H is the height of this rectangle. That's given by this length in the x direction. So that's the x coordinate on the higher end and the x coordinate on the lower end. So on the lower end it's 0. On the higher end it's going to be 1 over y. So H will be 1 over y. As for R, that's the distance from the axis of rotation. That's given by y. And so dr is given by dy. Now we need our bounds of integration. So bounds, we'll get y, r min is equal to y min, which is 1. Right, that's the smallest y value in this region. And r max is the max y value, which is 3. Okay. So now we will add in another page after this. Okay, so putting that all together, we have V I'm sorry, there's some technical issues going on here. V equals the integral from r min to R max of 2 pi HR dr. And in our case, that's from 1 to 3 of 2 pi times 1 over y dy. And what we get is 2 pi times the integral from 1 to 3 dy, which is just 2 pi times y evaluated from 1 to 3, or 4 pi. So that's a really nice way for that integral to come out, in my opinion. And we get a nice expression. 4 pi is the volume of this volcano-esque solid here. Now let's go to our next example, example 3. Let R be the region enclosed by y equals the square root of x and x equals 2y. Find the volume of the solid obtained by rotating around the line x equals 5. So the first thing we notice here is that the axis of rotation is neither the y nor the x-axis. It's x equals 5. So we're going to have to be careful about that. But otherwise, we proceed as normal. First thing we do is draw the region and the axis. Excuse me. Okay, so drawing this region, we have the sideways half parabola y equals square root of x. Okay. We usually draw that in blue. Let's try that. Blue. And then we have the line x equals 2y, which should look something like this. Okay, so we've got an intersection point up here, intersection point down here. If we want to know what those intersection points are, we have square root of x equals, well, we want to get the equivalent y, so we'll divide x by 2. X over 2, square both sides, we get x equals x squared over 4. And then that means x squared minus 4x equals 0, which in turn means x equals 0 or 4. Okay, so that means 0 here and 4 over here. And this is our region. Okay. The axis of rotation, though, is x equals 5. So that's on the edge of the page here. This is x equals 5. And this is where we're going to be rotating. Okay, so given that, the next step, draw a slice. Well, that is going to be parallel to the axis of rotation because we're using shells. So that's this guy. Okay. Now we want to label H, R, and dr. Okay, and this is where it gets a tiny bit tricky. So we're going to use, for our h, it's the height of the rectangle, which is square root of x minus x over 2, because that's the y coordinate of the lower point. R is going to be given by the distance from the line 5 to the point that we're at, so that's going to be 5 minus x. And putting the infinitesimal here, we'll get dr equals minus dx. Okay. Finally, in terms of the bounds, so R min corresponds to the smallest distance from the axis of rotation, which is from 5 to 4, or 1. And R max corresponds to the furthest distance, which is 5. So let's add in another page here to finish this integral. So we have all of the relevant variables. So we're going to compute the volume now. So we take v equals the integral from r min to r max of 2 pi h r dr, and this is given by the integral from, now some care has to be taken here, because even though r min is 1 and r max is 5, we're about to make a change of variables where r is going to become 5 minus x, dr is going to become minus dx, and so we need to also make sure that these bounds change corresponding to that. So the r min value corresponding to, the x value corresponding to r min equals 1 is x equals 4. And the r max value, sorry, the x value corresponding to r max equals 5 will be 0. Okay? So then we have 2 pi h, oh, and sorry, we have to replace the h as well. H is given by square root of x minus x over 2 times r dr, which is 5 minus x times minus dx. Okay, I'm going to pull out the minus 2 pi, but I'm going to get rid of the minus sign by just flipping the bounds of the integral. So now it's from 0 to 4. And I'll make a note. Cancel the minus sign by flipping the bounds. Okay, so now we can do a little more here. We can FOIL this out. We get 5 root x minus 5x over 2 minus x to the 3 halves plus x squared over 2, and this is all dx. Okay. Bring this to the next page. Okay. So next up, and we should probably get rid of this arrowhead. Okay. So let's continue to simplify. We have 2 pi. Everything in here we can just use the power rule, so that's not too bad. So we'll get 5x to the 3 halves divided by 3 halves minus 5x squared over 4 minus x to the 5 halves divided by 5 halves plus x cubed over 6, all evaluated from 0 to 4. Okay. Now we're just continuing to simplify. We have 10 x to the 3 halves over 3 minus 5x squared over 4 minus 2x to the 5 halves over 5 plus x cubed over 6. Now we can actually start evaluating. So a nice thing is that when the lower bound is 0, we don't have to, everything is going to evaluate to 0, so we just have to worry about 4. So 2 pi 10 times x to the 3 halves, the square root of 4 is 8. It is 2, so we can just turn that into 8 divided by 3 minus 5 times 16 divided by 4 minus 2 times, okay, it's 4 to the 5 halves, so that's 16 times 2, or 32, over 5, plus 64 over 6. Okay. And when you do out all the math, this comes out to I believe, 136 pi over 15. Okay. So pretty straightforward. Find your axis of rotation, find your region, label all of the different variables correctly, including the bounds, and the method of shells gets you to the volume of the solid you're interested in. Okay, thanks for your attention.